Hey guys, my name is IBM and I want to take you to lesson 6, I think. This is going to be lesson 6 of waves and superposition. And I think in lesson 6, we shall basically concentrate on concepts to do with electromagnetic waves, where we shall explore the regions of the electromagnetic spectrum, the 7 regions of the electromagnetic spectrum, and the properties of electromagnetic waves, how electromagnetic waves are produced, and some of the applications of some of the electromagnetic waves. I expect that this unit of electromagnetic waves was talked about in IGCSE. If you're doing triple physics or you're doing physics 0625, you must have explored electromagnetic waves in more detail. So we are going to just explore on the same concepts you mentioned about electromagnetic waves in IGCSE, and this time we shall just try to be very specific and deviate from some of the things you mentioned from in IGCSE so that we make this to be a little bit more advanced for AS levels. Do not forget, this is AS Physics 9702. But like I said, these tutorials may still be useful for other curricula such as AQA, such as IB, because physics remains the physics in all the across every curriculum. Only that the details to which concepts are taught the details to which concepts are being taught may be different, but it still remains the concepts of physics still remain the same. So let's start lesson 6, and we shall start from electromagnetic waves. This is actually 7.3. Remember, 7.1, we're looking at progressive waves and introduction to waves. In 7.2, I think we have talked about the Doppler effect. And in 7.3, we should explore electromagnetic waves. So this unit of electromagnetic waves, or this unit 7.3, is going to be concerned with the properties of electromagnetic waves, which, unlike mechanical waves, we saw that they can propagate through empty space. They can travel through a vacuum. Between 1931 and between 1831 and 1873, James Clerk Maxwell's crowning achievement was to show that the beam of light is a traveling wave of electric and magnetic fields, an electromagnetic wave to that effect. So Maxwell is remembered for having been able to show that light travels as electric and magnetic fields. This led to what we call electromagnetic waves. Of course, I know that it is not immediately obvious that light has any connection at all with electricity and magnetism and even waves. So it is not really very obvious for someone to connect electricity to magnetism and waves. However, these topics, as we mentioned earlier on, had been the subject of study by physicists for centuries before the connections between them became apparent. Before scientists started connecting waves, electricity, and magnetism, the start of these topics, a lot of physics had taken initiative to study most of these topics until a time came when they had to connect all the topics to come up with meaningful phenomena or to come up with meaningful explanations to different concepts of everyday life. So we know that an electric current always gives rise to a magnetic field. That is from your concepts of electromagnetic effects that you studied in IGCSE. So that if there is a current flowing in a conductor, there is a magnetic field around the conductor. That's what we call electromagnetism. And that's how we came up with an electromagnet, which you mentioned in the IGCSE. Similarly, if we have a changing magnetic field, if there is a changing magnetic field, then we can produce a current. And this is how uh, electricity is generated in most of the countries. Within the generator, there are just coils of wire and magnetic and large pieces of magnet or large poles of a magnet, where the coils of wire just rotate between the poles of a magnet, and this causes a change in the magnetic flux linkage that we shall mention, or you might have seen in A-level paper form, in a unit called magnetic fields. So a changing magnetic field will induce a current in a nearby conductor or in a nearby wire. So these observations led to the unification of the theories of electricity and magnetism. So we have seen that an electric current can cause a magnetic field around it, and a changing magnetic field can produce an electric current. So it means there must be a unifying factor between the theories of electricity and the theories of electromagnetic and the theories of magnetism, which led to the concepts of electromagnetic waves. So in Maxwell's time, in James Clerk Maxwell's time, I think visible light, ultraviolet, visible light, infrared, and ultraviolet form of light were the only electromagnetic waves known at that time. And later on, Heinrich Hertz then discovered what we today call radio waves, and he was able to verify that they also moved through the laboratory at the same speed as visible light. We now know today a wide spectrum of electromagnetic waves, and we know that the sun is actually the primary source, or the sun being the dominant source of these waves, which continually bathes us with all these regions of the electromagnetic spectrum every day. So the sun is the dominant source of the electromagnetic waves, which bathes us almost on a daily basis. So Clark was able also to show us that the speed of electromagnetic waves in a vacuum was not dependent on the frequency of the waves, but it's constant. And of course, the general theory of the general theory of relativity was also able to verify that everything else was relative, was relative to the position of the observer, apart from the speed of light, which was considered to be constant. So Clark was able to show that the speed of electromagnetic waves in a vacuum was actually not dependent on the frequency of the waves themselves, but it was a constant. So the speed was constant, which therefore meant that the frequency and wavelength would not still be constant, because we wouldn't have two quantities which were constant in the same expression. So Clark was able to verify that the speed of electromagnetic waves was so high, and it was constant in a vacuum. Of course, it would change in other media such as glass and so on and so forth, but it remained constant in a vacuum. So what is the nature of these electromagnetic waves? What is the nature of the electromagnetic waves? So when we talk about an electromagnetic wave, or when we talk about electromagnetic waves, we are talking about electric and magnetic fields interacting. How do they interact? They interact at right angles to each other, and they interact, or they travel perpendicular to the direction of propagation of the wave. So this animation here is actually demonstrating electromagnetic waves. They propagate, or when we talk about electromagnetic, we're talking about the electric field vector, or the electric fields and the magnetic fields interacting. So the electric field and the magnetic field interact in such a way that they are always at right angles to each other, and they propagate through space or through a vacuum perpendicular to the direction of propagation of the wave. For example, in this animation, blue is showing a vertical vibration in the vertical or in the Y, and red is showing vibration in the horizontal. But then the wave is traveling from, let's say, left to right. So it's like the electric field vector, which is the one in blue, and the magnetic field vector, which is the one in red, are vibrating perpendicular to each other and perpendicular to the direction of propagation of the wave energy. So that is how electromagnetic waves behave. So all electromagnetic waves are transverse in nature. They are transverse, and they are consisting of electric and magnetic fields which oscillate or vibrate, or which oscillate at right angles to each other and to the direction in which the wave is traveling. So an electromagnetic wave is made up of the electric and magnetic fields which oscillate perpendicular to each other and also perpendicular to the direction of propagation of the wave energy. So that is what we call an electromagnetic wave. That is their nature. The vibrations or the oscillations of the electric and magnetic fields are perpendicular to the direction of propagation of the wave energy. That is an electromagnetic wave. So many times we shall illustrate the electromagnetic waves just like this. To show oscillations which were perpendicular, the electric field vector or the electric field oscillating perpendicular to the magnetic field, and at the same time the electric and the magnetic field oscillate perpendicular to the direction of propagation of the energy, or perpendicular to the direction in which energy is being transferred. So this is the nature of electromagnetic waves. They are actually made up of electric and magnetic fields, which are oscillating perpendicular to each other and also perpendicular to the direction of propagation of the wave. So why do we call this to be transverse? Because these fields are oscillating perpendicular to the direction of propagation of the wave energy. That's why we call electromagnetic waves to also be transverse. Remember, for transverse waves, we say the particles vibrate perpendicular to the direction of propagation of the wave energy, or the direction of propagation of the wave. That was the nature of transverse waves. So we say that electromagnetic waves are actually transverse. What are some of the properties, therefore, of these electromagnetic waves apart from them being transverse? So electromagnetic waves have the following properties, or they have the following properties in common. Number one, remember all the properties of all other waves. They also apply to electromagnetic waves. However, we can try to specify them here. Electromagnetic waves, like I've mentioned, they are transverse. In other words, we have seen vibrations or oscillations perpendicular to the direction of propagation of the wave energy. Number two, electromagnetic waves are produced by oscillating charged particles. How does an antenna or transmitting antenna produce electromagnetic waves or radio waves? A transmitting antenna, when a current flows through the antenna, the current is due to the flow of the charge carriers, which is the electrons. So the electrons radiate energy around the antenna because of their oscillation. So electromagnetic waves are produced by oscillating charged particles, such as electrons. Number three, electromagnetic waves do not require any medium for their propagation. In other words, we know that these can go through a vacuum. Of course, they travel at the same speed, or the speed of light, which is 3 times 10 to the power of 8 meters per second in a vacuum. But because the speed is constant from v equals to lambda times f, if this is constant, it means their wavelength and frequencies vary. Of course, other factors of waves also also apply here, such as diffraction, reflection, refraction. You mentioned reflection and refraction in details in IGCSE. We may not mention them here. We shall only talk about diffraction later on. By the way, these also obey the principle of superposition that we shall see later on. Just like any other wave, these also obey the principle of superposition and therefore produce what we shall later on call interference patterns. So you might have mentioned interference in IGCSE, but not in much details. However, one property which makes them unique is the last property, which we are going to call polarization. In unit 7.4, that will be maybe in lesson 7, we shall see what we mean by polarization. Polarization is one of the properties, or is the major property, which makes electromagnetic waves different from all the other waves. So electromagnetic waves show what we call polarization, which is a property only unique to transverse waves. We cannot see longitudinal waves showing polarization. So transverse waves show polarization, and we shall explain what we mean by polarization in 7.4 or in lesson 7. Okay. So let us now explore the electromagnetic spectrum, having seen the nature of of electromagnetic waves as transverse waves, which consist of electric and magnetic fields oscillating perpendicular to each other and perpendicular to the direction of propagation of the wave energy. And having seen the properties of electromagnetic waves, let's now try to explore the electromagnetic spectrum. Of course, we know that the electromagnetic spectrum is divided into 7 regions based on the properties of electromagnetic waves in these regions. So the spectrum is divided into 7 regions, and these regions I think are given by Reed's mother is visiting Uncle Xavier's garden. So in order of increasing wavelength, the regions are gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. That is, in order of increasing wavelength, the wavelength increases from gamma rays to radio waves. In other words, radio waves have the greatest wavelength. I want you to note that since they all move at the same speed of light, increasing wavelength means decreasing frequency because V equals lambda times F, which means if V is the same, then frequency or wavelength is inversely proportional to the frequency. So if gamma radiations have the shortest wavelength, then they must be having the highest wavelength, or they must be having the highest frequency for that matter. If radio waves have the longest wavelength, then they must be having the lowest frequency or the smallest frequency. In order, therefore, of increasing frequency, we shall start with radio waves up to gamma rays. So gamma rays have the highest frequency and radio waves have the smallest frequency. So we today now regard all the types of radiation as part of the same electromagnetic spectrum, and the names given to the types of waves are simply for convenience in describing the region of the spectrum in which they lie. So some names may not hold their special meaning, or they may not hold their normal English meaning, just in case there's a name which has an English meaning. But these names are just are simply for convenience in describing the region of the spectrum in which they lie, apart from maybe the visible region, because these ones basically the visible region or the visible light is basically responsible for our own vision. So we are going to explore these radiations one by one in brief, but we shall not go into deep details, but we shall just explore them in brief. So let us start with the radio waves. Remember, we said the region has seven waves ranging from radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. The order of these waves can easily be recalled using a simple mnemonic that we shall talk about later on in more details. That is, Reed's mother is visiting Uncle Xavier's garden. So let's begin with the radio waves. Of course, the radio waves, these ones have a wavelength between, I think it's between 10 to the power of 4 up to 10 to the power of around 1, I think, around -1. So radio waves have wavelength between 10 to the power of 4 to around 0.1 meter or 10 to the power of -1 meters. Now, the range of these wavelengths is very important, but later on I will give you a clue on how to remember some of the estimate wavelengths for these regions. So, they have such a wavelength. These ones, just like the other waves, are as a result of charges oscillating or charges accelerating through conducting wires. That's why a radio transmitter can send radio waves into space, and the receiving antenna can also receive radio waves in space. So these ones are as a result of charges accelerating through conducting wires, and they are used especially in radio and television communication systems. So these ones, they are as a result of accelerating charges. Just like I mentioned, all electromagnetic waves are produced by oscillating charges. So even these ones are as a result of charges accelerating through wires or through conducting wires. And these ones are commonly used in radio and TV communication systems. Those are the radio waves. We shall not go into the details of these radio waves at this level. Number 2, let's talk about microwaves. The microwaves, these ones have wavelengths ranging from around 0.3 meters to around 10 to the power of minus 4 meters. By the way, you'll also note later on that there will be no clear boundary between one region of electromagnetic waves and the next region. Sometimes there will be a small overlap. So the microwaves have wavelengths ranging between 0.3 meters to around 10 to the power of minus 4 meters. And these ones are also generated by electronic devices where they are, of course, accelerating charges. They are also suited for radar systems. We saw this under Doppler effect, where the microwaves are used to track satellites, to track planes, and so on and so forth. So they are normally used for radar systems and for studying atomic and molecular properties of matter, including other applications such as microwave oven cooking, and so on and so forth. So the microwave ovens, satellite television, and telephones also use microwaves. So we have microwave oven cooking at home, satellite televisions, and telephones also use microwaves. Tracking planes, tracking satellites in space could rely on Doppler effect using microwaves. Microwave oven cooking, satellite television, and telephones commonly use these microwaves. That is the second region. Remember I said the wavelength is very, very important. The applications may not be very important because you mentioned them or you examined on them in IGCSE. Number 3 is the infrared. The infrared region, which has a wavelength between 10 to the power of minus 3 up to the largest wavelength of the visible spectrum, which is 7 times 10 to the power of minus 7 meters. That is the infrared radiation or the infrared waves. So the infrared waves, these ones are normally produced by molecules and room temperature bodies or room temperature objects. And they are already absorbed by most materials. So most materials absorb these radiations or these infrared. And what is the effect? Of course, when materials absorb these infrared radiations, their energy agitates atoms. In other words, their energy causes atoms to vibrate, thereby increasing their vibrational or translational motion, which results into increase in temperature. So these ones are produced by molecules and room temperature objects, but they are already absorbed by most materials, including yourselves. The infrared energy absorbed by a substance appears as internal energy or heat. So it is going to appear as internal energy or heat because the energy agitates atoms of the object, increasing their vibrational or translational motion, which results into temperature increase. So the infrared radiation is going to cause an increase in temperature. So many times when your body absorbs infrared, the temperature of the body increases. Infrared radiations also have applications in everyday life. We have what we call infrared photography, which you mentioned in IGCSE. I don't want to talk about it here. We have lasers. Many lasers use infrared radiation for transmission of information via lasers. For example, we have optic fibers use infrared radiation, especially for telecommunication and so on and so forth. Then we have electrical appliances such as the heaters and the grills, radiant heaters, and we have the grills. We have the remote controllers of televisions. We have intruder alarms. These ones all use infrared radiations. But like I said, applications may not be very important at this level because you explored them in IGCSE. The number 4 should be visible light. Number 4 should be visible light. Of course, visible light is part of the electromagnetic spectrum, which is responsible for our vision. It's the one where the human eye can detect or the human eye is sensitive to. Of course, the human eye will not see the radio waves, microwaves, and infrared. Neither will the human eye see the X-rays or the gamma rays. Or it may not even see the ultraviolet. So visible light is the part of the electromagnetic spectrum that the human eye can detect. Of course, we know how light is produced, even though we don't want to go into the details of how light is produced, but it is produced by rearrangement of electrons in atoms and molecules. So note that all electromagnetic waves are involving oscillating or accelerating charges. So light is also produced by rearrangement of electrons in atoms. As electrons rearrange themselves, maybe moving from a higher energy level to a lower energy level, as we shall mention in quantum physics, the electrons emit photons, and the photons constitute what we call light or visible light. The wavelength of visible light range between 7 times 10 to the power of -7 meters up to 4 times 10 to the power of -7 meters. Now, this range of visible light is the most important one because it's going to help us to estimate the wavelengths of all the other regions. 7 times 10 to the power of -7, I think that is the same as 700 nanometers. And 4 times 10 to the power of -7, I think that is the same as 400 nanometers. So many times you will see the wavelength quoted as 700 nanometers up to 400 nanometers, with 700 being red and 400 being violet. So visible light ranges in that has those wavelengths um, that range as the wavelengths. However, the sensitivity of the human eye is a function of wavelength, being a maximum at a wavelength of about 5 times 10 to the power of -7 meters. You notice that 5 times 10 to the power of -7 is almost the average of 7 times 10 to the power of -7 and 4 times 10 to the power of -7. So it's like the human eye is a function of wavelength. The sensitivity of the human eye is a function of wavelength, and it has its average or its maximum at an average of all the 7 colors, or at an average of the wavelength of all the 7 colors. Of course, with this in mind, it is now not surprising anymore that tennis balls have a yellow-green color or yellowish-green color, because yellowish-green will have a wavelength of approximately 5 times 10 to the power of -7 meters. That is 5 at 7 plus 4 divided by 2. I think this is going to be 5.5 times 10 to the power of -7 meters. So this is approximately yellowish green wavelength. So the tennis ball, because it moves very fast, to be easily seen by the human eye, it is painted or it is always in yellowish green color. When we talk about monochromatic light, for example, which is going to be very common in applications, it is normally used in lasers, and we know what lasers can do. So visible light can be monochromatic, as we shall see later on. Of course, monochromatic meaning light of a single wavelength. Of course, if the wavelength is constant and if the wavelength is the same and yet the speed is the same, it means the frequency is the same. And light of a single wavelength or single color is going to be called monochromatic. Mono meaning one, chromatic coming from chrome or chroma, which means color. Monochromatic, single color or same one color. So that is visible light. What is very important about visible light is the range of the wavelengths that I have mentioned here. The number 5, I think number 5 is ultraviolet light. Ultraviolet light or ultraviolet waves covers wavelengths ranging from this is violet up to around 10 to the power of -10 meters. So the range of wavelengths is 4 times 10 to the power of -7 to around 10 to the power of -10 meters. Of course, the sun is an important source of the UV light, which is the main source of sunburns. That's why during summer, you're always applying sunscreen lotions because of the UV light. You're trying to filter out the UV light from reaching on your skin. So sunscreen lotions are transparent to visible light, but they absorb the UV light. So this would prevent sunburns. UV rays have also been implicated in the formation of eye diseases such as cataracts, a clouding of the eye lens, or a clouding of the lens inside the eye. This is an eye condition which could be as a result of the destruction of the eye lens due to exposure of your eyes to UV light. That's why many times during summer you would prefer, or it would be better you put on sunglasses when you're going out in the scorching when you're going out in in the sun. So most of the UV light from the sun is absorbed by what we call the ozone, or the ozone layer, or the ozone molecules in the Earth's upper atmosphere, in a layer called the stratosphere. So the stratosphere is where we find the ozone. The ozone's purpose is to shield us from excess UV by converting the high energy UV radiation to infrared radiation, which in turn warms up the stratosphere. So most of the UV from the sun does not reach us because the stratosphere has a layer of, or has molecules, or ozone molecules, which protects us from excess UV radiations from reaching us. So in addition to the ozone, we also add sunscreen lotions to our bodies to try and filter out most of these, or the stray UV rays which pass through the ozone to reach the Earth's surface. So the purpose of the ozone is to filter out the UV light, but that's not for physics, it's just for geography. Let's also talk about X-rays. Of course, X-rays, we talk about X-rays in paper 4 again. I think that will be quantum physics. X-rays have a wavelength between 10 to the power of minus 8 meters to around 10 to the power of 10 to the power of minus 12 meters. I want you to notice the overlap. I want you to notice the overlap. We saw that for UV light it was between 4 times 10 to the power of minus 7 meters up to around 10 to the power of minus 10 meters. And we are seeing that for X-rays it is 10 to the power of minus 8 to around 10 to the power of minus 12. Many times students quote the estimate to be 10 to the power of minus 11 meters as the wavelength of X-rays. So you'll always see 10 to the power of minus 11 very commonly stated as the wavelength of X-rays. But there's always an overlap. There's no clear boundary between one wavelength, one region to another. So the most common sources of X-rays is stopping of high energy electrons upon bombarding a metal target. So still here we have oscillating or accelerating electrons, which when they collide with a metal target, they decelerate rapidly and produce X-rays. We shall see this in quantum physics. X-rays are used as a diagnosis tool in medicine. Of course, you have heard of the X-ray radiography. When you break your bones, you might have undergone an X-ray scan. Also, they are used in the treatment for certain forms of cancer. So, diagnosis or X-ray radiography, treatment of cancer. Because X-rays damage or destroy living tissues and organisms, care must be taken to avoid unnecessary exposure or overexposure. We shall talk about X-rays in more details under medical physics, that is production and use in medical physics of these X-rays. By the way, X-rays are also used in the study of crystal structure because X-ray wavelengths are comparable to atomic separation distance in solids, which is about 0.1 nanometers. We shall also talk about this in quantum physics. Because the wavelength of X-rays is approximately the same as the interatomic spacing, X-rays can easily undergo diffraction when passed through a solid, when passed through crystal structures. And because they can undergo diffraction, then this helps us to study crystal structures or different crystal structures. So those are the X-rays. Then on the other hand, or finally, we should talk about the gamma rays. Gamma rays which we shall also mention in medical physics in the PET scan, are electromagnetic waves emitted by radioactive nuclei such as cobalt and cesium, and during certain nuclear reactions. So during certain nuclear reactions, such as the reactions involving cobalt and cesium, X-rays can also be, gamma rays can be generated, but we shall talk about this in more details in medical physics. Of course, in medical physics, in the PET scan, we shall see that when a positron meets an electron, or when a positron meets an electron, gamma rays or a pair of gamma rays is emitted, which gamma rays are responsible for generating the image during a PET scan, as we shall see. The gamma rays have wavelengths between 10 to the power of minus 10 to 10 to the power of minus 14. Many times students state 10 to the power of minus 12 as the typical, or 10 to the power of minus 13 meters as the typical wavelength of gamma rays, but there is no clear boundary between these wavelengths. So these ones, what is special about gamma rays is that they are highly penetrating, and they would produce serious damage when absorbed by living tissues. Just like X-rays, gamma rays are highly penetrating because they have the highest frequency. Since they have the shortest wavelength, they're highly penetrating, they're very energetic, and therefore they can easily damage, um, or they can easily produce damage when absorbed by living tissues. And consequently, therefore, those working near such dangerous radiations must be protected with heavily observing materials, such as thick layers of lead. So you mentioned this in IGCSE still, that if you are dealing with radiation such as X-rays and gamma rays, which are very dangerous, um, you must protect yourselves by using thick layer lead or coats made out of thick layer lead materials, because we know that lead can really reduce X-rays or gamma radiations to a certain extent, because a thick layer of lead would easily absorb or prevent the further penetration of gamma rays and X-rays. A few things we need to note here. The first one, a simple mnemonic to remember the order of the electromagnetic spectrum in order of either decreasing or increasing frequency, or in order of decreasing wavelength and increasing frequency, could be Reed's mother is visiting Uncle Xavier's garden, where we take out the first letters. Reed's R for radio waves, mother M for microwaves, I for infrared, V for visible light, U for ultraviolet, X for X-rays, and G for gamma rays. So this means radio waves have the longest wavelength. So this is in the order of, when I move from reeds to gamma to garden, it means I'm starting with the highest wavelength to the shortest wavelength. So radio waves have the longest wavelength, but remember, wavelength is inversely proportional to frequency, so they have the lowest frequency. Gamma rays will have the shortest wavelength, but they will have the highest frequency. It is very important to note that. Also, I want you to note the wide ranges of frequencies and wavelengths. There is no sharp dividing point between one type of the wave and the next. No sharp dividing point exists between one type of wave and the next, or one type of region and the next. So there is an overlap. Also, I want you to remember that all forms of the various types of radiations are produced by the same phenomenon. We say they are produced by accelerating charges. That's why in almost every case, charges have been involved, either accelerating or accelerating charges being decelerated or being stopped, and so on and so forth. So in summary, the region of the electromagnetic spectrum would look somehow like this. So ranging from gamma rays, X-rays, ultraviolet, then we have the visible light, where we have the 7 colors. The 7 colors or the visible light is ranging from, here we have violet up to red. Virgin in bed, get your organ ready. So the visible region has these 7 colors which make up the visible spectrum. Then we have infrared, microwaves, and radio waves. So the radio waves have the longest wavelength. Of course, we know that wavelength is the distance moved by a wavefront in one cycle, or the distance between two successive peaks. And you notice that this diagram shows that as I move from the right hand side to the left hand side, the distance between the peaks becomes smaller, and it is shortest on the end of the gamma rays. So you should have that in mind. Now you may ask yourself, how do I recall these wavelengths? Because you will be asked to make estimates of some of these wavelengths. You do not need to recall exactly the exact values of these wavelengths, but you can always have an estimate. It is easier to estimate this. However, you need to know the wavelength of visible light. So visible light ranges between 7 times 10 to the power of -7 meters up to 4 times 10 to the power of -7 meters. So this is red and this is violet. And in here we have the other colors of the rainbow. After red, we have infrared. So on this side we have radio waves, microwaves, and infrared, because here we have the visible spectrum. After the visible spectrum, we have ultraviolet, we have X-rays, and we have gamma rays. So if I want to find the wavelength of infrared, I'll just add a +2 onto the power of infrared. So this would be 10 to the power of -5 meters. The number in front doesn't matter. If I want to estimate the wavelength of microwaves, I'll add a +2 onto the power of infrared. So this becomes 10 to the power of -3 meters. Whenever I add a 2 onto the left hand side or towards the radio waves, whenever I add a 2, I will get an approximate wavelength in that region. If I want radio waves, I'll add a +2 onto this and I'll get -1 meters. But remember, radio waves start from 10 to the power of 4 up to around 10 to the power of -1. On the other side, I subtract a -2 from the power of 10. For example, from 10 to the power of -7, when I subtract 2, I'll get 10 to the power of -9 meters. Of course, that will fall in our ultraviolet. When I subtract 2, I'll get 10 to the power of -11 meters. That will fall under X-rays. When I subtract 2, I'll get 10 to the power of -13, which becomes gamma rays. So if I know the wavelengths of the visible light or the visible spectrum, I can predict the wavelengths on both sides of the visible spectrum. And if I know the wavelengths on both sides, if I can find the wavelength of both sides of the visible spectrum, then using V equals to lambda times F, you have already predicted the wavelength. The speed V is constant, which is 3 times 10 to the power of 8. Then I can always predict the frequency. You should be able to do that. In summary, this table summarizes the main principles that we need to talk about about these radiations. So gamma radiations or gamma waves, we have seen the range of the wavelengths. This is supposed to be 10 to the power of -14, not 16. Of course, some of the uses: cancer treatment, medical imaging like the PET scan, and so on and so forth. X-rays, we have seen the range of wavelengths. Cancer treatment, medical imaging. Ultraviolet, we have also seen ultraviolet up to around 10 to the power of -9. These are vitamin D synthesis. Visible light, that is for vision, we know the range of wavelengths. Infrared, We know the range of wavelengths. Of course, infrared are normally used for Bluetooth, TV remotes, and so on and so forth, laser light, intruder alarms, and so on and so forth, infrared photography, and so on and so forth. Then microwaves. The microwaves are normally used for Wi-Fi, satellite and television communication, satellite communication, telephone, and so on and so forth. Then the radio waves normally used for communication, TV and radio communication. Like I said, the uses are not very important for this level because you mentioned them in IGCSE. So those are some of, that is the summary of these 7 regions of the electromagnetic spectrum. As an assignment, I'm giving an assignment. So in your assignment, you can come up with a personal mnemonic to remember the order of the electromagnetic spectrum. So what do I mean by a mnemonic? It can be a statement which helps you to remember the order. Like I gave mine, Reed's mother is visiting Uncle Xavier's garden. Your mnemonic can be in order of increasing wavelength or in order of increasing frequency. The order doesn't matter. Then 2, each of you should research in more detail and prepare a presentation on one of the regions of the electromagnetic spectrum. In your discussion, you must include, you can include the range of frequencies and wavelengths. That one has been discussed mostly. You can include the speed in different media. In a vacuum, it is the same, but you can explore the speed in different media. You can include the method of production, how they are produced. You can include how they are detected. And you can also include the use in different spheres of interest. So this can be part of your research work. You try to look at each of the regions, the 7 regions ranging from Reed's mother is visiting Uncle Xavier's garden. You can try to carry out that research. Okay, let's just run through a few quick self-check questions. Red light of wavelength 700 nanometers in a vacuum travels into glass where its speed decreases to 2 times 10 to the power of 8 meters per second. Determine the frequency of the light in a vacuum. So frequency F is going to be V divided by lambda, where V in a vacuum is 3 times 10 to the power of 8 divided by lambda, which is 700 times 10 to the power of 7 minus 7. So this is going to be 3 exponent 8 divided by 700 exponent minus 7. So the frequency is going to be 4.3 times 10 to the power of 12 hertz. Then the frequency and the wavelength in the glass. So frequency is going to be equal to 2 times 10 to the power of 8 divided by the speed divided by the wavelength, which is not known. But remember, sorry, the wavelength is the frequency and wavelength in the glass. Remember, the frequency of a wave depends on the source. So it means the frequency is still going to be 4.3 times 10 to the power of 23 hertz. It's only the wavelength which is going to change, because a smaller distance may now be covered. So it means the wavelength is going to be changed, but the number of cycles is going to remain the same. So the frequency is going to be 4.3 times 10 to the power of 12 hertz, because the frequency of a wave depends on the source. And then the wavelength is going to be V divided by the frequency, which is going to be 2 times 10 to the power of 8 divided by the frequency, which is going to be 4.3 times 10 to the power of 12. So this is going to be 2 exponent 8 divided by 4.3 exponent 12. So this is approximately 4.65 times 10 to the power of minus 5 meters. I'm going to change it to nano, divide this by 1 exponent negative 9 It is very big. I will just leave it like that. A sinusoidal electromagnetic wave of frequency 40 megahertz travels in free space in the x direction as shown. Determine the wavelength and the period of the wave. So wavelength is going to be v divided by f. V is 3 times 10 to the power of 8 divided by f, which is 40 times 10 to the power of 6. So 3 exponent 8 divided by 40 exponent 6. So this gives you 7.5 meters. Determine the wavelength and the period. Of course, period is equal to 1 over frequency, which is 1 divided by 40 exponent 6. So the frequency period is 2.5 times 10 to the power of minus 8 seconds. In many kitchens, a microwave oven is used to cook food. The frequency of the microwave is on the order 10 to the power of 10 hertz. The wavelengths of these microwaves are on the order of, so we can find the wavelength. Lambda is equal to V divided by F. V is 3 times 10 to the power of 8 divided by 10 to the power of 10, which is going to be 3 exponent 8 divided by exponent 10. So this is 0.03 in meters. So when I multiply this, to make this a whole number, it becomes, I have to multiply this by 100, which becomes 3 centimeters. So this one is going to be of the order centimeters. Then calculate the frequency in megahertz of radio wave of wavelength from 250 meters. So you can just press your calculator and find the frequency from V over lambda. Then you just divide by 10 to the power of 6 to find it in megahertz. Let me just press my calculator. V is 3 exponent 8 divided by the wavelength, which is 250. Then I divide this by mega is power 6, so I divide by 1 exponent 6. So the answer here should be 1.2 megahertz. You can verify. Calculate the wavelength in nanometers of X-ray wave of frequency 2 times 10 to the power of 18. You can verify if that is correct. Calculate the frequency of red light of wavelength 6.5 times 10 to the power of minus 7. Frequency is equal to 3 times 10 to the power of 8 divided by the wavelength, which is 6.5 times 10 to the power of minus 7. You can try to verify. Calculate the wavelength of microwaves of frequency 8 gigahertz. Remember, giga is 10 to the power of 9. So the frequency is 8 times 10 to the power of 9. So you can just substitute in the equation and find the wavelength. A beam of red light has an amplitude of 2.5 times the amplitude of a second beam of the same color. Calculate the ratio of the intensities of the waves. So remember, intensity is directly proportional to amplitude squared. So we want to calculate the ratio of the intensities of the waves. I don't have enough space here, but I will use the bottom here. For the first beam, let's say its intensity is I equals to K times A squared. For the second one, I'll quote I1 is going to be K, and its amplitude is 2.5 times. A beam of red light has an amplitude that is 2.5 times the amplitude of a second beam of the same color. So let's say I1 is 2.5 times A, but this should be squared. The amplitude is 2.5 times the first amplitude, but when you square, so I'll get the ratio. Let's say I1 divided by I2, divided by I is going to be K into 2.5A squared divided by K A squared. So the ratio is going to be equal to, because A squared cancels, you remain with 2.5 squared, which is 6.25. So the ratio is going to be 6.25. State one property of electromagnetic waves that is not common to other transverse waves. Of course, traveling in a vacuum is a property of electromagnetic waves which is not common to other transverse waves. But the rest, polarization, all other transverse waves can undergo polarization. But like water waves cannot travel through a vacuum, so they need a material medium because they are mechanical. Then the 7 regions of the electromagnetic spectrum are represented by blocks labeled A to G. In the figure below, a typical wavelength for the visible region D is 500 nanometers, so this must be visible. Name the principal radiation and give a typical wavelength for each of the region B, E, F. So this is increasing wavelength. So this must be radio waves because radio waves have the highest wavelength. So Reed's mother is visiting Uncle Xavier's garden. So this is radio, micro, infrared, visible, ultraviolet, X-rays, gamma rays. So B is X-rays, E is infrared, F is micro, so X-rays, we have seen the typical wavelength. X-rays is about 10 to the power of minus 11. Infrared could be 10 to the power of minus, I think, 5. Microwaves can be 10 to the power of minus 3. Remember the simple method I gave. You know that the visible light ranges from red to violet. Red is 10 to the power of minus 7. 7 times 10 to the power of minus 7. Violet is 4. Violet is 4 times 10 to the power of minus 7. So on the other side, I go on subtracting minus 2. The power of, we go on saying minus 2 the other side. On this side, we say plus 2. This side you are coming from red up to radio waves. The other side you are moving from violet up to gamma. All the waves in the spectrum shown above can be polarized. To explain the meaning of polarization, we are going to explain polarization, but this one means confining the vibrations of the electric field vector in only one plane. We shall explore and explain polarization in more details, but the vibrations, if vibrations of a wave can be made to be on only one plane, in only one plane, we say that the wave has been polarized. For each of the following frequencies, state the type of electromagnetic radiation it corresponds to. So 200 kilohertz. Of course, it is hard for us to tell the type by looking at the wavelengths by the frequencies, but we can first of all convert the frequencies to the wavelengths. Remember, wavelength is going to be V over F, which will be 3 times 10 to the power of 8. I'll start with the first one. The first one is 200,000. 200,000. So let me see the wavelength. 3 exponent 8 divided by 200,000. So this is 1,500 meters. Of course, this is radio waves. So you can check this one, you can check that one, and you can check that one. For each of the following wavelengths measured in a vacuum, state the type of electromagnetic radiation it corresponds to. 1 kilometer, that must be radio. 3 centimeters, that could be radio. This is 3 centimeters is 3 divided by 100. 0.3, this is micro. 5,000 nanometers is 5,000 exponent negative 9 is the same as 5 times 10 to the power of minus 6. Then power minus 6, I think this is infrared. 500 nanometers, I think this is visible. 50 nanometers is 50 exponent negative 9. This is 5 times 10 to the power of minus 8, which is UV, ultraviolet. Then 10 to the power of minus 12 is X-rays, or it can also be gamma rays. And lastly, a radio wave of frequency 10 power 5 Hz is used to carry a sound wave with a frequency 10 to the power of 3 Hz. The wavelength of this radio wave is on the order of, so this is the wavelength, this is the frequency of the radio wave which is used. So let's find the wavelength is going to be the speed 3 times 10 to the power of 8 divided by the frequency, which is 10 to the power of 5. So 3 exponent 8 divided by exponent 5. So this is 3,000 meters, which is the same as 3 kilometers. So this one is of the order kilometers. When light or other electromagnetic radiation travels across a given region, what is it that oscillates? Of course, this is charges. It is the charges which oscillates. What is the fundamental source of electromagnetic radiation? That is accelerating charges. Accelerating or oscillating charges. What are the wavelength ranges in A? The AM radio band, the frequency ranges from 540 to 1600. And in B, the FM band ranging from 88 to 108 megahertz. We just find V or lambda equals to V divided by F, and then we substitute. I'll just put in my calculator. V is 3 exponent 8 because FM and AM, these are radio waves. So it is 3 exponent 8 divided by 540,000. So this is going to be 556 meters up to 3 exponent 8 divided by 1600,000. This is 188 meters. So that is the range. Then you can also check this one as an assignment. We just use the formula V lambda is equal to V over F, where this is 3 times 10 to the power of 8 divided by the value of F. I think that should be the end of lesson 6, and see you in lesson 7. Bye bye. Oh, I answered these questions, by the way. So here we have oscillating electric and magnetic fields. What travels across a region? Oh, that is electric and magnetic fields. Sorry for that. And what is the fundamental source? I think these are accelerating charges. I think that was a mistake I made. What travels across a region? It is the charges. I mean, it is the energy which moves because it is a progressive wave, but it is the electric and magnetic fields which oscillate. That is a mistake for question 15. I think I'm very tired. Until next time, bye bye.